am going to how these two techniques will be useful for low power consumption. In VLSI, low power is main parameter. Okay, main parameter and main constraint. So how this will be helpful for low power consumption? So pipelining and parallel processing. If we consider the delay, if delay is less, speed is high. We can say delay less means speed is high. Okay, and power consumption is another constraint. So here we can analyze either speed or propagation delay. Both are one and the same. They are representing the same performance in a system. When delay is less, speed is high. Okay, so low propagational delay means high speed, and power consumption also low. These two are expected in any circuit. Now, this is the standard formula for propagation delay. This is the first one is the standard formula for propagation delay. So you have to remember this: C into V divided by beta V naught minus Vt whole square. Okay, so C into V, V naught means output. V naught is the supply voltage, not output, supply voltage. V naught is the supply voltage. Vt is threshold voltage. Okay. So C charge means charging time of the capacitances. Whatever capacitances are there, what is the denotes the capacitor. Whatever capacitance it is charged. And K represents a constant parameter. It is a function of, it is a parameter which is a function of W by L ratio, oxide capacitance and mu permittivity, all these three. Okay, so here this is the formula for propagation delay. This is the general, without pipelining, without parallel processing. Okay, propagation delay. This is sequential circuit or without parallel processing and pipelining. This is the formula for propagation delay. In this, C means capacitance. Whatever internal capacitances are there, how much it is present. Then V naught is supply voltage and K is function of permittivity, W by L ratio, oxide capacitance, internal. Okay, initial small values, all these are small values. K is a constant and then Vt is threshold voltage. In this equation, these are the parameters present. Supply voltage, threshold voltage, a constant parameter K, and C means capacitance. Okay, this is propagation delay. Now power consumption without parallel processing, without pipelining, power consumption formula is C total into V naught square F. C total into V naught square F. C total means total capacitance of the entire circuit. Total capacitance in the entire circuit. V naught means already we know supply voltage, and then F is the clock frequency of the circuit. What is the frequency of operation? Okay. So these two formulas we have to remember. Power consumption means total capacitance into V naught square F. Okay, power consumption means total capacitance into V naught square F, and propagation delay means CV naught divided by K into V naught minus Vt whole square. Okay, these two formulas we have to remember. These formulas are without pipelining and without parallel processing. Here I will write without pipelining, without parallel processing. Okay, same thing, without pipelining and without parallel processing. These are the propagation delay and power consumption for a basic FIR filters. For a basic filter. Now I am going to apply pipelining. What happens to these two parameters? Then parallel processing. What happens to these two parameters? Okay. So now I am going to pipelining technique. So when pipelining is applied, the first one, propagation delay is there. This capacitance, charging capacitance value will change. Okay, this value will change. By what level? In the pipelining, what is the M value? How many multipliers you are dividing? If you see, M level pipelining is used. What is this M value? Okay, and this charge, capacitance charge will reduce by that amount compared to the original. Original previous formula is C charge into V naught. Now it will become C charge divided by M into V naught. C charge will decrease. That M is nothing but number of levels in the pipeline structure. Okay. And coming to remaining parameters, it remains same. It will remain same. You see the formula here, and supply voltage also. The meaning of this, the capacitances will decrease. Capacitance will decrease. C charge divided by M, which means time taken for charging or discharging will decrease. Okay. So time taken, it is decreasing. So when time taken is decreasing, supply voltage also can be decreased. Supply voltage also can be decreased. Okay, this is the thing in pipelining technique. So low power application means supply voltage you are decreasing. So power consumption can be decreased by this method. Okay. So the capacitance, the time taken for charging, discharging, it will decrease based on how many levels are used in the pipelining. So formula will change accordingly. In this formula, this is without pipelining, the propagation delay. Okay, propagation delay without pipelining. Now with pipelining, what happens? With pipelining, what happens? That C charge will change. C charge divided by M. Supply voltage also, wherever V0 is there, it will become beta V0. Okay, two things is happening. C is changing to C by M, and V0 is changing to beta V0. V0 is changing to beta V0. This through two things we are incorporating in the previous formula. Where the charge is there, that becomes divided by M. Where the supply voltage is there, that becomes multiplied with beta. This beta value is less than 1. Now supply voltage initially how much required? We need not provide that much supply voltage. A fraction of the supply is enough. So this beta factor is less than 1. Okay, a lesser supply voltage is sufficient. Now, when we equate these two in the pipelining, the clock frequency and the sampling frequency are same. In the pipelining, clock frequency and sampling frequency are same. And here, whatever the time we got in 3.13 and 3.14, whatever RHS is there, if we equate them, what happens? This equation will come. 3.15 will come. 3.15. Okay. So what I am doing here, just 1 minute. So what I am trying to do, in the first case I had C V0 divided by K into V0 minus Vt whole square first time. Okay. This is without pipelining. With pipelining, what I had C by M. Okay. V0 will become beta V0 divided by K times beta V0 minus Vt whole square. When you equate this, what will happen? The C will get cancelled, V0 will get cancelled. Okay. And K also will get cancelled. We will be left out with beta times V0 minus Vt whole square. It is equal to beta by M and V0 minus Vt whole square. Cross multiply. So here M will go to the left side. Beta and V0 minus Vt whole square. It is equal to beta times V0 minus, somewhere I am doing wrong. Here it is beta times and Now here I have tried beta by m. This is correct. Left side I have tried beta inside. No. Left side I have tried beta inside. Now it is okay. Beta V naught minus Vt whole square. Okay. So right side it will be like this only. The left side m into beta V naught minus Vt whole square. Right side beta into V naught minus Vt whole square. Okay. So same thing is here. The final equation. You see this line. I'm trying to explain this line. Just the previous two equations when you equate. This will come. Okay, m into beta V naught minus Vt whole square. Left side m into beta V naught minus Vt whole square. Right side beta into V naught minus Vt whole square. So now this will become, when we substitute the value of supply voltage, threshold voltage and m value, it will become a quadratic equation in terms of beta. Beta is fraction of supply voltage what we are applying when pipeline is introduced. Okay, fraction of supply voltage. This fraction is less than 100%. Without pipelining, what supply voltage we have given, that is 100%. With the pipelining, this beta is less than 1. So fraction means it is less than 1. So one equation will come. We have to calculate beta value. After calculating beta value, we have to substitute in power consumption. What is power consumption formula? C into V naught square F. Okay. So C into V naught square F. This is without pipelining. With pipelining, tell me what will happen. With the pipelining, what will happen? This is C total. Okay, this is C total. With the pipelining means two things will change. One is time taken for charging. Second one is V naught will become beta V naught. So here C charge is not present. However, in the calculation of total capacitance, there will be change. And V naught will become beta V naught. Okay, V naught will become beta V naught whole square into F. That is the propagation power consumption. That is the power consumption. You can see here, this is the power consumption formula. C is as it is, beta V naught whole square into F is present. Okay, C into beta V naught whole square into F. This is the power consumption when pipelining is introduced. Okay, so now what all we have discussed, I have put a tabular comparison, tabular column. You can see here, without pipelining means first column. These are the basic formulas. Without pipelining means first column. These are the basic formulas. With the pipelining means these are the formulas we derived. Okay.